What if I told you that the most violent events in the entire universe are also the most essential for your existence? Right now, somewhere in the cosmos, a star many times more massive than our sun is breathing its last breath. In its final moment, it will unleash more energy in seconds than our sun will produce in its entire lifetime. This is not just destruction. This is creation. This is the story of supernovae, the cosmic forges that built the world around you and the very atoms within you. Are you ready to witness the most beautiful death in all of existence? Not all stars are created equal. While our sun is a comfortable middleweight champion that will burn steadily for billions of years, there exist stellar giants that live fast and die spectacularly. These are the massive stars, born with 8 times the mass of our sun or more, sometimes reaching hundreds of solar masses. From the moment they ignite their nuclear furnaces, they are on a countdown to an explosive end. Can you imagine a star so massive that it burns through its fuel millions of times faster than our own sun? These giants are the architects of the cosmos, and their story begins in the densest regions of space. These massive stars form in the hearts of giant molecular clouds, where gravity pulls together vast amounts of hydrogen and helium. The more massive the star, the more intense the gravitational pressure at its core. And with greater pressure comes greater temperature. While our sun's core reaches about 15 million degrees, the core of a massive star can exceed 100 million degrees even in its youth. This intense heat drives nuclear fusion at a furious pace. Where our sun will live for 10 billion years, a star 50 times more massive might last only a few million. It is a trade that seems unfair, but it is this very intensity that makes their death so spectacular and so vital. In the core of these massive stars, hydrogen fuses into helium, releasing tremendous energy that pushes outward against the relentless inward pull of gravity. This is the eternal battle of a star's life, a perfect balance between explosion and collapse. But massive stars do not stop at helium. When the hydrogen in the core is exhausted, the core contracts and heats up even more, hot enough to fuse helium into carbon and oxygen. Then carbon into neon, neon into oxygen and magnesium, and so on. Each stage produces heavier elements and lasts for a shorter time. You might spend your entire life within a single one of our sun's heartbeats, and yet a massive star would have already cycled through multiple stages of fusion in that same moment. As the star ages and creates heavier elements, its internal structure becomes like an onion with layers upon layers of different elements undergoing fusion at different depths. Hydrogen fuses in a shell around the helium core. Helium fuses in a shell around the carbon-oxygen core. This continues inward, creating shells of increasingly heavier elements: silicon, sulfur, calcium, and more. Each layer burns at different temperatures and pressures, creating a complex and beautiful internal architecture. Can you picture it? A star as a living cathedral of nuclear fire, each chamber burning with its own unique light. And yet, despite this incredible power, the star is marching inevitably toward its final act. The visible surface of a massive star tells a story of the violence within. Unlike our calm yellow sun, these giants often appear blue or white from their extreme temperatures. Their surfaces are turbulent and chaotic, with massive convection cells carrying heat from the interior. Powerful stellar winds blow off huge amounts of material, creating vast nebulous shells around the star. Some massive stars pulse and vary in brightness, expanding and contracting like a slowly beating heart. If you could somehow stand on a planet orbiting such a star, you would be bathed in intense ultraviolet radiation, and the sky would be dominated by a sun so large it might fill your entire field of view. But such a planet could never exist in peace, for the star's end is always near. Many massive stars do not live alone. They are often part of binary or multiple star systems, locked in an eternal dance with companion stars. These stellar partnerships can be breathtakingly beautiful, with stars orbiting so close that they actually share material between them. Streams of plasma flow from one star to another, creating glowing bridges of matter across the void. In some systems, the more massive star evolves faster and may explode first, leaving behind a neutron star or black hole that then feeds on its companion. These are some of the most dynamic and energetic systems in the universe, cosmic laboratories where extreme physics plays out on a grand stage. And when one of these giants finally explodes, its companion will feel the shockwave across the gulf of space. Throughout its life, a massive star is preparing for its death. The intense radiation pressure blows powerful stellar winds into space, enriching the surrounding region with elements created through fusion. These winds can carry away a significant fraction of the star's mass, creating beautiful bubbles and shells of glowing gas around the star. When you look at regions of active star formation through a telescope, you can see these effects everywhere. The blue giants illuminate vast clouds of gas with their ultraviolet light, causing them to fluoresce in spectacular displays of color. They are cosmic lighthouses, their brilliance announcing both their presence and their impending doom. The universe is never still, and these stars are proof that even in the quiet of space, everything is constantly changing and evolving toward its ultimate fate. Deep in the core of our massive star, something profound is happening. After millions of years of fusion, the star has created an iron core at its very center. Iron is special. It is the most stable element, sitting at the peak of the nuclear binding energy curve. Using iron into heavier elements does not release energy, it consumes energy. For the first time in the star's life, fusion in the core actually takes more energy than it produces. The nuclear fire that has held up the star against gravity for so long is now draining the star's strength rather than replenishing it. Can you feel the tension building? The star is living on borrowed time, and the clock is ticking faster with every passing moment. The end is no longer millions of years away. It is now measured in days. The iron core grows rapidly as the silicon shell above it continues to fuse and add more iron to the center. Within a matter of days, the core can reach a mass of about 1.4 times the mass of our Sun. This is a critical threshold known as the Chandrasekhar limit. Up to this point, the electrons in the core have been supporting the star through what is called electron degeneracy pressure. But there is a limit to how much mass this quantum pressure can support. Once the core exceeds this limit, not even the strange rules of quantum mechanics can hold back gravity. The core has become too heavy to support itself. The final moment is now hours away, and nothing in the universe can stop what comes next. If we could watch the star's core in these final hours, we would see temperatures rising to billions of degrees. The iron nuclei are vibrating with such intensity that they begin to break apart in a process called photodisintegration. High-energy gamma rays slam into iron atoms and literally tear them back down into helium and free neutrons. This process absorbs tremendous amounts of energy, further undermining the core's stability. At the same time, electrons and protons are forced together by the extreme pressure, combining to form neutrons and neutrinos in a process called neutronization. The neutrinos, those ghostly particles that barely interact with matter, stream out of the core, carrying away even more energy. The core is being hollowed out from within, and gravity is about to win its ultimate victory. And then, in less than a second, it happens. The core collapses. not slowly, not gradually, but in a catastrophic implosion that defies imagination. The entire iron core, 1.4 solar masses of the densest matter outside a black hole, collapses from the size of Earth to the size of a city in a fraction of a second. Material falls inward at speeds approaching 1/4 the speed of light. As the core collapses, density rises to unimaginable levels. Atomic nuclei are crushed together until they touch. There is no more empty space between atoms. The matter becomes so dense that a teaspoon of it would weigh as much as a mountain. This is neutron degeneracy, matter at its ultimate limit. Have you ever wondered what happens when an unstoppable force meets an immovable object? You are about to witness exactly that. At the very center, a neutron star is being born. This is an object so extreme that it challenges our understanding of physics. Imagine the mass of 1.5 suns compressed into a sphere only 20 kilometers across. A single cubic centimeter of neutron star matter contains as much mass as a mountain. The surface gravity is 200 billion times stronger than Earth's. The magnetic fields are the strongest in the universe, trillions of times more powerful than any magnet you have ever encountered. And the neutron star is spinning, rotating hundreds of times per second as conservation of angular momentum takes the slow rotation of the original core and compresses it into a frenetic whirl. This is matter at the absolute edge of what is physically possible before it collapses into a black hole. But the formation of the neutron star is not the end. It is the beginning of something far more spectacular. When the collapsing core reaches nuclear density, it suddenly becomes rigid. Material is still falling inward at 1/4 the speed of light, and now it hits this impenetrable wall of neutron matter. The infalling material bounces. The core rebounds like a cosmic spring, launching a shockwave outward through the collapsing layers above. This is the moment of the supernova explosion, but it is not as simple as a bounce. The shockwave begins to stall as it plows through the dense overlying material. For a brief moment, the fate of the explosion hangs in the balance. Will the shockwave fail and fall back, or will it succeed in blowing the star apart? The answer lies in the neutrinos. In the first second after collapse, the neutron star releases an almost unimaginable burst of neutrinos. More neutrinos than have been emitted by all the stars in the galaxy in the last year pour out of the tiny, hot neutron star. Though neutrinos normally pass through matter as if it were not there, the material around the core is so dense that some of them are captured. They deposit their energy into the stalled shockwave, reviving it and giving it the push it needs to continue its journey outward. It is one of nature's most elegant solutions. The ghostly particles that usually ignore everything become the crucial ingredient that turns a collapse into an explosion. The fate of the star is sealed. The shockwave will reach the surface, and when it does, the universe will witness one of its most spectacular events. The shockwave races outward through the star at tens of thousands of kilometers per second. As it passes through each layer, it compresses and heats the material to billions of degrees. The carefully arranged onion structure that the star spent millions of years creating is torn apart in an instant. Silicon is heated and fused into iron in seconds. Oxygen and neon ignite in explosive fusion as the shockwave passes. Elements that would have taken the star thousands of years to create through normal fusion are synthesized in the blink of an eye. The shockwave is not just destroying the star. It is transforming it, cooking up new elements as it goes. Every heavy element you have ever encountered was likely created in a moment like this one. The gold in your jewelry, the iodine in your thyroid, the uranium in the Earth's core, all were born in stellar fire. It takes hours for the shockwave to traverse the interior of the giant star, but when it finally reaches the surface, the universe takes notice. The surface of the star, which had been glowing peacefully with the light of a supergiant, suddenly erupts with the fury of a billion suns. The temperature of the surface rises from a few thousand degrees to hundreds of thousands of degrees in minutes. The light output increases by a factor of 1 billion or more. A single supernova can briefly outshine an entire galaxy of hundreds of billions of normal stars. If you were observing from a nearby star system, you would see the star suddenly brighten to an intensity that would cast sharp shadows even from millions of kilometers away. The brightness would continue to increase for days or weeks, turning night into day across any planets unfortunate enough to be nearby. The outer layers of the star, no longer gravitationally bound to the core, are accelerated to speeds of thousands of kilometers per second. Imagine the mass of several suns worth of material, all being thrown into space at once. The kinetic energy involved is staggering, equivalent to the total energy output of the sun over its entire 10 billion year lifetime, all released in a matter of days. This ejected material expands outward in all directions, creating an expanding bubble of stellar debris that will eventually span light years. The expansion is not uniform. Instabilities in the explosion create complex structures with jets, knots, and fingers of material extending in different directions. From our vantage point, this creates some of the most visually stunning objects in the cosmos. Each supernova is unique, like a cosmic fingerprint left behind by a dying star. Within the expanding debris, nuclear reactions continue. The explosion has created conditions extreme enough for the rapid neutron capture process, or R process, to occur. In the intense neutron flux near the core, atomic nuclei capture neutron after neutron, building up heavier and heavier elements faster than they can decay. This is how nature creates the heaviest elements, those beyond iron on the periodic table. Gold, platinum, uranium, thorium, and all the rare earth elements owe their existence to this process. The wedding ring on your finger contains atoms that were assembled in seconds during a supernova explosion billions of years ago. You are wearing a piece of stellar death transformed into something beautiful. Is there a more poetic connection between humanity and the cosmos? The supernova does not just create heavy elements. It creates energy across the entire electromagnetic spectrum. Gamma rays pour out of the explosion site, carrying away tremendous amounts of energy. X-rays follow as hot gas cools slightly. Visible light, the brilliance we could see with our eyes, represents only a small fraction of the total energy output. Infrared and radio waves will continue to be emitted for years or even millennia after the initial explosion. If you could see in radio waves, a supernova would appear as a bright beacon that slowly fades over centuries. And then there are the neutrinos. The neutrino burst from the supernova races ahead of the light, arriving hours earlier. Any civilization with neutrino detectors would receive a warning that something spectacular is about to appear in their sky. From Earth, when we detect a supernova in a distant galaxy, we are seeing light that left the explosion thousands, millions, or even billions of years ago. The star that created it may have exploded before life even arose on Earth. We are witnesses to ancient violence, cosmic time capsules delivering news of events from the deep past. Astronomers rush to observe each new supernova, capturing its light curve and spectrum, learning about the nature of the explosion and the star that created it. Each supernova teaches us something new about stellar evolution, nuclear physics, and the chemical enrichment of the universe. They are not just pretty lights in the sky. They are laboratories where we can test our understanding of physics under conditions we could never create on Earth. And they are beautiful precisely because they are real, natural phenomena occurring on the largest scales imaginable. Not all supernovae are created equal. The details of the explosion depend on the mass of the progenitor star, its composition, and whether it was part of a binary system. Some supernovae are symmetric and relatively smooth. Others are wildly asymmetric, with jets of material shooting out from the poles. Some eject their outer layers cleanly, while others leave behind complex, tangled structures. The explosion can be affected by the star's rotation, its magnetic fields, and the composition of its core. This diversity is what makes each supernova unique and beautiful in its own way. When we look at the different supernova remnants scattered across our galaxy and beyond, we are seeing snapshots of different types of stellar deaths, each one telling a slightly different story of how a star met its end. After the initial explosion, the supernova enters a phase that can last for months or even years. The expanding debris continues to shine brightly, powered initially by the tremendous heat of the explosion. But as the ejecta expands and cools, a different energy source takes over. Many supernovae are powered in their later phases by the radioactive decay of unstable isotopes created in the explosion. Nickel decays into cobalt, which then decays into iron, releasing gamma rays with each transformation. These gamma rays heat the expanding gas, causing it to glow. The light curve of the supernova, the way its brightness changes over time, tells us about the amount and distribution of these radioactive elements. It is like watching a cosmic nuclear battery slowly discharging, illuminating the debris field for months after the initial flash. During this afterglow phase, the supernova slowly fades from view. What was once brighter than a galaxy dims to the luminosity of a single bright star, then fades below naked eye visibility. Telescopes continue to track the supernova for months, watching as its spectrum evolves and changes. The outer layers expand and cool, allowing us to see deeper into the ejecta. Lines of different elements appear and disappear in the spectrum as conditions change. Oxygen lines strengthen as the debris cools. Iron lines emerge from the inner regions. Calcium and sulfur make themselves known. Each element leaves its signature in the light, telling us about the nuclear processes that occurred during and after the explosion. We are reading the chemical autobiography of a dying star, written in the language of light. As months turn into years, the supernova enters its final visible phase. The ejecta has expanded to the point where it becomes transparent, and the radioactive power source has largely decayed away. The supernova dims below the threshold of most telescopes. But this is not the end. The expanding bubble of debris is about to encounter the surrounding interstellar medium, and when it does, a new phase will begin. The supernova remnant will light up once again, not from the explosion itself, but from the interaction between the fast-moving ejecta and the stationary gas around the original star. This phase can last for tens of thousands of years, creating some of the most beautiful structures in the galaxy. The death of the star continues to echo through space long after its light has faded from view. At the center of the expanding debris, something remarkable remains. The neutron star, born in the collapse of the core, continues its existence. Some neutron stars are remarkably quiet, simply cooling slowly over billions of years. But others are among the most active objects in the universe. If the neutron star is rotating rapidly and has a strong magnetic field aligned just right, it becomes a pulsar, sweeping beams of radiation across space like a cosmic lighthouse. Others may have powerful winds of particles streaming away, creating glowing bubbles within the supernova remnant. And in rare cases, if the original star was massive enough, there may be no neutron star at all. The core may have continued collapsing past the neutron star phase, forming a black hole. At the heart of beauty lies an invisible singularity, a tear in the fabric of space-time itself. Some supernovae have additional features that make them even more spectacular. If the star shed material in the millennia before it exploded, creating shells or rings around itself, the supernova blast wave will eventually catch up to this material. When the fast-moving ejecta slam into these older, slower-moving shells, the collision creates brilliant arcs and rings of light. The most famous example is Supernova 1987A, which occurred in the Large Magellanic Cloud. As the years passed after the explosion, astronomers watched as the blast wave lit up a ring of material around the star, creating one of the most iconic images in astronomy. The ring glows with incredible brightness, heated to millions of degrees by the passing shock. It is a stellar monument, a glowing memorial to the star that once was. The energy released by a supernova does more than just light up the surrounding space. It pushes on the interstellar medium, compressing gas and potentially triggering the formation of new stars. The shockwave can travel for hundreds of light years, leaving a trail of compressed, heated gas in its wake. In regions where massive stars form in clusters, the supernovae of the most massive stars can create superbubbles, vast cavities hundreds of light years across, carved out of the interstellar medium. These bubbles are visible in galaxies across the universe as holes in the gas distribution, often surrounded by rings of compressed material where new stars are being born. Destruction and creation are inseparable partners in the cosmic dance. The death of one generation of stars seeds the birth of the next. In our own galaxy, the Milky Way, supernovae occur roughly every 50 years on average. That means that since humans have been recording history, hundreds of supernovae should have been visible to the naked eye from Earth. Ancient astronomers did record some of these events, noting the appearance of new stars that shone brightly for weeks or months before fading away. The records from Chinese, Japanese, European, and Arabic astronomers have allowed us to match some supernova remnants to historical events. Each recorded supernova is a connection between past and present, between human observers and cosmic phenomena. When we look at the Crab Nebula, we're seeing the remnant of an explosion witnessed and recorded in the year 1054. The same photons that amazed observers nearly 1,000 years ago continue to travel through space, bringing us information about that ancient event. Now we enter perhaps the most beautiful phase of the supernova story. Decades or centuries after the explosion, the expanding debris has slowed down as it plows through the interstellar medium. The thin gas between the stars acts as a brake, but it also creates something remarkable. Where the debris meets this gas, shockwaves form, heating both materials to millions of degrees. The shocked gas emits light across the spectrum, especially in X-rays from the hottest regions and invisible light from slightly cooler areas. Complex structures begin to emerge. Filaments, sheets, and knots of glowing gas trace out the architecture of the explosion. This is the supernova remnant phase, and it can last for 50,000 years or more. These are among the most spectacular objects visible to our telescopes. Each supernova remnant is unique, shaped by the nature of the explosion and the environment it expands into. Some are nearly spherical shells, smooth and symmetric. Others are wildly asymmetric, with jets, fingers, and bubbles extending in all directions. The Veil Nebula, part of the Cygnus Loop remnant, shows us exquisitely thin sheets of shock-heated gas glowing in shades of red from hydrogen, blue from oxygen, and yellow from sulfur. The structures are so delicate they look like they could be torn apart by a gentle breeze, yet they are moving at hundreds of kilometers per second and contain the mass of multiple suns. Beauty and violence coexist in these cosmic clouds. When you look at a supernova remnant through a telescope, you are seeing the frozen shockwave from an explosion that happened when your great-great-great ancestors were just beginning to tell stories around fires. The colors we see in supernova remnants tell us about the physical conditions in the gas. Red light comes primarily from hydrogen alpha emission, created when hydrogen atoms are ionized by the shock and then recombine. Green and teal light comes from doubly ionized oxygen, requiring higher temperatures to produce. Blue might come from singly ionized sulfur. By combining images taken through different filters, astronomers can create views that map temperature, density, and composition across the remnant. These are not arbitrary colors chosen for aesthetics, though the results are undeniably beautiful. They are scientific data transformed into visual form. The beauty is a side effect of the physics, but what glorious side effect it is. Nature creates art without even trying. Within supernova remnants, cosmic rays are accelerated to tremendous energies. At the shock fronts where the expanding debris meets the interstellar medium, particles can be accelerated to nearly the speed of light. These cosmic rays, mostly protons and heavier nuclei, will travel through the galaxy for millions of years. Some of them will eventually strike Earth's atmosphere, creating cascades of secondary particles. Every few minutes, a particle that was accelerated in a supernova millions of years ago passes through your body, a tiny messenger from a long-dead star. Supernova remnants are the galaxy's particle accelerators, far more powerful than anything we can build on Earth. They help maintain the population of cosmic rays that fill interstellar space, influencing everything from the chemistry of molecular clouds to the evolution of life on planets. The Crab Nebula is perhaps the most famous supernova remnant, and it shows us something special. At its heart is a pulsar, a rapidly spinning neutron star that was born in the explosion of 1054. This pulsar spins 30 times per second and emits powerful beams of radiation and a wind of energetic particles. The pulsar wind creates a bubble within the remnant, filling it with a web of glowing filaments powered by the neutron star's rotational energy. In X-ray images, the crab appears as a blue-white cloud surrounding the pulsar, constantly changing and evolving. The outer red filaments are the actual supernova debris, expanding at thousands of kilometers per second. The Crab Nebula shows us that supernova remnants are not static fossils. They are dynamic, evolving systems, constantly changing on timescales from days to centuries. Another magnificent remnant is Cassiopeia A, the youngest known supernova remnant in our galaxy. The explosion occurred about 350 years ago, though no one on Earth seems to have recorded it, likely because intervening dust dimmed the light. Today, Cass A is one of the brightest radio sources in the sky and has been studied extensively at all wavelengths. The images reveal an incredibly complex structure. The debris is moving so fast that we can actually see it expanding over timescales of just a few years. Hot gas glowing in X-rays shows us the blast wave. Infrared images reveal warm dust created in the explosion. Optical images show the fastest moving knots of ejecta. Each wavelength tells a part of the story. By combining all these views, we can reconstruct what happened in that distant explosion and understand the star that created it. As supernova remnants age, they gradually fade and disperse. Over tens of thousands of years, the shockwave continues to slow as it entrains more and more interstellar material. Eventually, the shocked gas cools to the point where it no longer emits visible light efficiently. The remnant merges with the general interstellar medium, becoming indistinguishable from ordinary molecular clouds and HII regions. The material from the supernova is now mixed with the surrounding gas, enriching it with heavy elements. Future generations of stars will form from this enriched material. They will have higher metallicities, more heavy elements to work with, and planets forming around those stars will have the building blocks necessary for complex chemistry and perhaps for life. The supernova remnant has completed its mission, returning the star's ashes to the cosmic ecosystem from which new stars and planets will emerge. Let us now turn to perhaps the most profound legacy of supernovae. Everything in the universe heavier than lithium was created inside stars or during supernova explosions. The primordial universe, emerging from the Big Bang, contained only hydrogen, helium, and traces of lithium. Every other element on the periodic table was synthesized later in stellar interiors or explosive events. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of these were created by stars and distributed by supernovae. When Carl Sagan said we are made of star stuff, he was not being poetic or metaphorical. It is literal scientific truth. You are the universe made conscious, atoms from long-dead stars organized into patterns that can think and wonder about their own origins. Oh, how remarkable is that? During the normal life of a massive star, fusion creates elements up to iron through a process called stellar nucleosynthesis. Hydrogen fuses to helium, helium to carbon and oxygen, and so forth through the periodic table. Each step releases energy and creates new elements. But iron is the end of the line for normal fusion. Creating elements heavier than iron requires energy input rather than releasing energy. So how do we get all the heavy elements we see around us? The answer lies in supernovae and other explosive events. During the explosion, there is suddenly an enormous flux of neutrons available and tremendous energy to drive reactions that would not normally occur. In these extreme conditions, nuclei can capture many neutrons rapidly, building up into heavier and heavier elements before they decay. This is how we get gold, platinum, uranium, and all the rare elements that make our technology possible. The process by which supernovae create heavy elements involves multiple mechanisms. The S process, or slow neutron capture process, occurs in the late stages of stellar evolution before the explosion. Neutrons are captured one at a time over long periods, allowing unstable isotopes time to decay before capturing more neutrons. This creates about half of the elements heavier than iron. The R process, rapid neutron capture, occurs in the intense neutron flux during a supernova or neutron star merger. Neutrons are captured so quickly that extremely neutron-rich nuclei are created, which then undergo chains of beta decays to reach stability. The R process creates the other half of heavy elements, including most of the heaviest elements like gold and platinum. There is also the P process, driven by proton capture in the supernova, creating rare proton-rich isotopes. Nature uses every available mechanism to forge elements. The distribution of elements created by a supernova tells us about the conditions during the explosion. Elements like oxygen and magnesium are created throughout the star and dominate the ejecta by mass. Silicon and sulfur come from the deeper layers. Iron and nickel come from the innermost regions near the core. The heaviest elements come from the most extreme environments. By studying the spectra of supernova ejecta and remnants, we can map out where each element was created and test our theoretical models. The observations match theory remarkably well, confirming our understanding of stellar nucleosynthesis. We can read the periodic table like a history book, each element telling us about the conditions that created it. When you look at a sample of gold, you are looking at atoms that were forged in the most extreme explosion a massive star can produce. The enrichment of the galaxy with heavy elements is a gradual process that has taken billions of years. The first generation of stars, forming from primordial gas with no heavy elements, created the first metals through supernovae. These elements mixed into the surrounding gas, slightly enriching it. The second generation of stars formed from this slightly enriched gas, lived their lives and exploded, adding more heavy elements. Each subsequent generation formed from more metal-rich gas. Our Sun is a relatively late generation star, forming about 4.6 billion years ago from gas that had already been enriched by countless previous generations of supernovae. This is why our solar system has substantial amounts of heavy elements. It is why Earth has an iron core, a silicate mantle, and surface water. It is why complex molecules could form and life could emerge. We owe our existence to billions of years of stellar death and rebirth. Different elements serve different purposes in the universe and in our lives. Carbon is the backbone of organic chemistry, able to form long chains and complex molecules. Nitrogen is essential for amino acids and DNA. Oxygen is necessary for water and respiration. Iron is crucial for hemoglobin and the cores of planets. Rare earth elements enable our modern electronics. Every element has its role, and every role traces back to the nuclear furnaces of stars and the explosive deaths of the most massive ones. The device you might be using to watch this video contains dozens of different elements, each with its own stellar origin story. The gold contacts in the circuitry were likely created in a neutron star merger. The silicon in the chips came from a dying star's fusion processes. The plastic casing contains carbon and hydrogen from the Big Bang, processed through multiple generations of stars. Your technology is a museum of cosmic history. The process of cosmic chemical enrichment continues today. Right now, massive stars throughout the universe are nearing the ends of their lives. Within the next second, several stars in the observable universe will explode as supernovae. Each explosion adds a few solar masses of heavy elements to its galaxy's interstellar medium. Over billions of years, this adds up to significant enrichment. Galaxies that have been forming stars for longer are generally more metal-rich than younger galaxies. By studying the chemical composition of stars in different galaxies and at different cosmic epochs, we can trace the history of element production across the universe. We are watching cosmic evolution in action, the universe slowly transforming itself from simple to complex, from hydrogen and helium to the rich diversity of matter we see today. And we are part of that story, conscious participants in the universe's journey of self-discovery. Supernovae do more than just create and distribute elements. They are also sculptors of galactic structure and triggers for future star formation. When a supernova explosion plows into the surrounding interstellar medium, it does not simply dissipate. The shockwave compresses the gas ahead of it, increasing its density. In some cases, this compression can trigger the gravitational collapse of gas clouds that were previously stable. Dense regions within molecular clouds, jostled by the passing shock, can tip over the threshold into collapse and begin forming new stars. In this way, the death of one star can trigger the birth of thousands of new ones. It is a cosmic cycle of death and rebirth, where each ending is also a beginning. The universe wastes nothing. Every ending creates opportunities for new beginnings. Our own solar system may owe its existence to a supernova. When astronomers study the isotopic composition of the oldest materials in our solar system, meteorites that formed in the solar nebula 4.6 billion years ago, they find evidence of short-lived radioactive isotopes. These isotopes decay so quickly that they should have all disappeared long before the solar system formed, yet they were present in the early solar nebula. The most likely explanation is that a nearby supernova exploded just as our solar system was beginning to form. The shockwave from that explosion may have triggered the collapse of the gas cloud that became our sun and planets, and also injected fresh radioactive isotopes into the forming system. If this is true, then we owe our very existence not just to supernovae in general, but to one specific stellar explosion that happened billions of years ago in our cosmic neighborhood. In regions where massive stars form in groups, sequential supernovae can create complex patterns of star formation. The first star to die explodes as a supernova, triggering collapse in nearby clouds. These new stars include their own massive members. A few million years later, when the next generation's massive stars die, they explode, triggering yet another generation. This creates a cascade of star formation propagating through a molecular cloud complex over tens of millions of years. We can see evidence of this sequential star formation in many star-forming regions. Young stars of different ages are arranged in patterns that reflect the passage of supernova shockwaves through the region. Star formation is not a random, isolated process. It is connected across time and space by the violent deaths of massive stars. Each generation of stars plants the seeds for the next. The energy input from supernovae also regulates star formation on galactic scales. If too many stars form too quickly, the resulting supernovae can heat and disperse the cold gas needed for more star formation, temporarily shutting down the process. This negative feedback mechanism prevents galaxies from converting all their gas into stars too quickly. Conversely, in galaxies where star formation has slowed, gas can accumulate and cool, eventually triggering new bursts of star formation. The balance between star formation and supernova feedback helps determine the evolution and appearance of galaxies. Galaxies with vigorous ongoing star formation tend to be blue, colored by hot, young, massive stars. Galaxies where star formation has ceased tend to be red, containing only older, cooler stars. Supernovae are thus key regulators of galactic evolution, controlling how quickly galaxies build up their stellar populations. In the densest regions of molecular clouds where multiple supernovae may have occurred, the cumulative effect can be dramatic. The overlapping remnants create superbubbles, vast cavities of hot, low-density gas surrounded by shells of swept-up material. These superbubbles can be hundreds of light-years across, dominating the structure of the galactic disk. The hot gas inside the bubble can remain at millions of degrees for millions of years, emitting X-rays and preventing star formation in the interior. But the shell around the bubble becomes dense and cool, a perfect site for new star formation. We can see superbubbles in our own galaxy and in nearby galaxies, recognized by their distinctive appearance in multi-wavelength observations. They are monuments to generations of stellar death, vast structures that show the power of supernovae to reshape their surroundings on truly enormous scales. Some superbubbles can grow so large that they break out of the galactic disk entirely, creating chimneys that vent hot gas into the galactic halo. This process, called galactic fountains, can transport heavy elements from the star-forming disk into the halo, where they mix with more pristine gas. Eventually, this enriched gas cools and falls back onto the disk, bringing its enhanced metallicity with it. The cycling of gas between the disk and halo, driven by supernova feedback, is an important part of galactic ecology. It helps distribute heavy elements throughout the galaxy and can affect the global star formation rate. When we model galaxy evolution on computers, we must include this feedback, or our simulations produce galaxies very different from what we observe. Supernovae are not just local events. They influence the evolution of entire galaxies. Even the magnetic fields that thread through galaxies owe their structure partly to supernovae. The expanding supernova remnants can amplify magnetic fields through compression and turbulent motions. These amplified fields are then carried away by the cosmic rays that the supernovae accelerate, spreading throughout the galaxy. The galactic magnetic field influences many processes, from cosmic ray propagation to the formation of stars and planets. By creating turbulence and amplifying fields, supernovae help maintain the magnetism that pervades interstellar space. Everything is connected. The death of a star ripples out through space and time, affecting the galaxy for millions of years after the explosion. Supernovae are not discrete events that happen and end. They are ongoing influences that shape the cosmos on the largest scales. And through it all, the beauty persists. Even in destruction, even in the most violent events imaginable, nature creates art. Millennia, humans have watched the sky and recorded unusual events. Ancient Chinese astronomers were particularly diligent, maintaining records of astronomical phenomena for thousands of years. When a new star appeared in the sky, they called it a guest star and carefully noted its position, brightness, and duration. Many of these guest stars were supernovae occurring in our galaxy. The supernova of 1054, which created the Crab Nebula, was recorded by astronomers in China, Japan, and the Arab world. They described it as bright enough to be visible during the day for 23 days. At night, it could be seen for nearly 2 years. Think about that. For 2 years, people could look up and see a star where none had been before, slowly fading away. What must they have thought? What stories did they tell about this celestial visitor? In 1572, the great Danish astronomer Tycho Brahe observed a supernova in the constellation Cassiopeia. This event, now known as Tycho's supernova, was so bright that it was visible during the day and became one of the brightest objects in the night sky. The supernova challenged the prevailing Aristotelian worldview that the heavens were unchanging and perfect. Tycho made careful measurements of the supernova's position and showed that it was beyond the moon, in the realm of the fixed stars. This observation helped pave the way for the scientific revolution. A stellar explosion, occurring thousands of light years away, influenced the development of human thought and science. The supernova remnant can still be observed today, a bubble of hot gas and energetic particles expanding into space, forever linked to the astronomer who observed its brief brilliance. In modern times, astronomers eagerly await each new supernova discovery. Professional surveys constantly scan the sky, looking for new transients. Amateur astronomers also contribute, with some dedicated individuals discovering multiple supernovae over their lifetimes. When a new supernova is detected, alerts go out to observatories around the world and in space. Telescopes of all types quickly slew to observe the new event, gathering spectra and light curves that will help characterize the explosion. Time is critical because supernovae evolve rapidly, especially in the first days and weeks. The data gathered from supernova studies has contributed enormously to our understanding of stellar evolution, nuclear physics, and cosmology. The discovery of accelerating cosmic expansion, one of the most important findings in modern cosmology, came from observations of distant supernovae. These stellar explosions are not just beautiful, they are tools for understanding the universe. The most famous recent supernova occurred in 1987 in the Large Magellanic Cloud, a small galaxy that orbits the Milky Way. Supernova. 1987A was the closest supernova visible to the naked eye since 1604, and it was studied in unprecedented detail. For the first time, astronomers identified the progenitor star in pre-explosion images, confirming it was a blue supergiant. Neutrino detectors on Earth. This was the first and still the only detection of supernova neutrinos, confirming our theoretical models. Over the following years and decades, astronomers have watched as the supernova remnant evolved, eventually seeing the blast wave light up a ring of material around the star. SN 1987A has provided a unique laboratory for studying supernovae in real time, transforming our understanding of these events. Supernovae have also taught us about the expansion of the universe itself. In the late 1990s, 2 teams of astronomers used observations of distant Type Ia supernovae to measure how the expansion rate of the universe has changed over cosmic time. Type Ia supernovae occur when a white dwarf star accretes matter from a companion and exceeds a critical mass, exploding with a remarkably consistent brightness. This makes them excellent standard candles for measuring distances across the universe. The teams expected to find that the expansion was slowing down due to gravity. Instead, they found that the expansion is accelerating. This discovery implied the existence of dark energy, a mysterious component that makes up about 70% of the universe. The discovery was so profound that it earned the 2011 Nobel Prize in Physics. Who would have thought that exploding stars could reveal the ultimate fate of the cosmos? Modern telescopes have revealed supernovae across the entire observable universe. The Hubble Space Telescope has captured images of supernovae in galaxies billions of light-years away. The James Webb Space Telescope is now finding supernovae at even greater distances during the universe's childhood. Ground-based telescopes equipped with adaptive optics can resolve details in nearby supernova remnants with exquisite clarity. Radio telescopes map the distribution of relativistic particles in remnants. X-ray observatories reveal the hottest gas and the radiation from pulsars. Infrared telescopes see through the dust to find newborn stars in compressed regions. Gamma-ray telescopes detect the highest energy processes. At every wavelength, in every corner of the sky, supernovae and their remnants reveal new wonders. The universe is perpetually renewing itself through stellar death, and we are privileged to witness it. Looking forward, the next generation of telescopes and surveys will revolutionize supernova science. Projects like the Vera Rubin Observatory will discover thousands of supernovae every night, allowing statistical studies of rare subtypes. Gravitational wave detectors may catch the collapse of a stellar core directly, giving us information about the interior of the explosion that light cannot provide. Neutrino observatories are being upgraded to better catch the next galactic supernova. When a star explodes in our galaxy, we will be ready. We will detect the neutrinos hours before we see the light. We will point every telescope we have at it within minutes. We will watch the light curve evolve in real time. We will see the debris slam into surrounding material. The next galactic supernova will be the most studied astronomical event in human history. And it could happen tomorrow, or in 100 years, or perhaps even while you are watching this video. The universe does not wait for us to be ready. Not all supernovae are created equal, and astronomers have developed a classification system to categorize the different types based on their spectra and light curves. The primary division is between Type 1 and Type 2 supernovae. Type 2 supernovae show hydrogen in their spectra and result from the core collapse of massive stars, the process we have been discussing. Type I supernovae lack hydrogen and come in several subtypes. Type Ia result from exploding white dwarfs in binary systems. Type Ib and Ik are actually core collapse supernovae from massive stars that lost their hydrogen envelopes before exploding. Each type has its own characteristics, its own typical brightness, and its own rate of occurrence. This diversity tells us that stars can die in multiple ways, each beautiful and violent in its own right. The cosmos is creative even in destruction. Type Ia supernovae deserve special attention because they are fundamentally different from core collapse events. They occur in binary systems where a white dwarf star, the remnant of a sun-like star, accretes material from a companion. As the white dwarf gains mass, it approaches the Chandrasekhar limit of about 1.4 solar masses. Near this limit, the conditions in the white dwarf's core become extreme. Eventually, carbon fusion ignites not in the center but slightly off-center. The flame spreads through the white dwarf in a runaway process, completely incinerating the star in a thermonuclear explosion. Unlike core collapse supernovae, which leave behind a neutron star or black hole, Type Ia supernovae completely destroy the white dwarf. Nothing remains but expanding debris. These events are slightly less energetic than core collapse supernovae, but more consistent in their brightness, making them valuable distance indicators for cosmology. Among core collapse supernovae, there is significant diversity based on the properties of the progenitor star. Type IIP supernovae show a distinctive plateau in their light curves that lasts for months as the expanding photosphere cools. These come from red supergiants that retained their hydrogen envelopes. Type I-Isle supernovae show a linear decline in brightness and come from stars that lost some but not all of their hydrogen. Type 2 IB supernovae show a transition from hydrogen-rich to hydrogen-poor spectra and come from stars that lost most of their hydrogen envelope. Type IB supernovae lack hydrogen but show helium from stars stripped of hydrogen. Type IB supernovae lack both hydrogen and helium from the most stripped massive stars. Each of these types represents a different evolutionary path to the same explosive endpoint. The diversity of supernovae reflects the diversity of massive star evolution. Some supernovae are even more extreme. Superluminous supernovae can be 10 to 100 times brighter than normal supernovae, outshining entire galaxies at their peak. The power source for these exceptional events is still debated. Some may be powered by the rotational energy of a rapidly spinning magnetar, a neutron star with an extremely strong magnetic field. Others might involve pair instability, a process where gamma rays in the star's core become so energetic that they create matter. Antimatter pairs, disrupting the star's stability. Superluminous supernovae are rare, but when they occur, they are spectacular. They can be seen across most of the observable universe, making them potential beacons for studying the early cosmos. If a superluminous supernova occurred in a nearby galaxy, it would briefly be one of the brightest objects in the night sky, visible even from light-polluted cities. At the most extreme end of stellar death are gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. Some long-duration gamma-ray bursts are associated with a special kind of core collapse supernova called a collapsar or hypernova. In these events, the core of an extremely massive, rapidly rotating star collapses to form a black hole. Material spiraling into the black hole forms an accretion disk, and powerful jets of matter and energy are launched along a rotation axis at nearly the speed of light. If these jets are pointed toward Earth, we see a gamma-ray burst, a brief but incredibly intense flash of gamma rays followed by a longer-lived afterglow. The visible supernova that accompanies the gamma-ray burst can be unusually bright and energetic. These are the death throes of the most massive stars in the universe, events so extreme they challenge our understanding of physics. Some stars may die in ways that do not produce traditional supernovae at all. Recent observations suggest that some massive stars may undergo failed supernovae, where the core collapses, but the explosion fizzles out, unable to blow off the outer layers. In these cases, the material falls back onto the core, which continues collapsing directly into a black hole with little to no visible explosion. The star simply disappears from view, fading away rather than going out in a blaze of glory. This may actually be the fate of a significant fraction of the most massive stars. Nature does not always choose the most spectacular option. Some endings are quiet, a massive star winking out of existence with barely a whisper. Even these silent deaths have their own profound beauty in their subtlety and mystery. The study of supernova diversity is an active area of research. Each new discovery potentially reveals a new subtype or challenges our existing classification scheme. Unusual supernovae that do not fit neatly into standard categories are particularly valuable because they hint at physical processes we have not yet fully understood. Some supernovae show evidence of strong interaction with dense circumstellar material, creating bright, long-lived transients. Others show multiple peaks in their light curves, suggesting complex energy sources or geometries. Each oddity is a puzzle to be solved, a chance to refine our understanding of stellar death. The universe is more diverse and creative than our theories, constantly surprising us with new variations on the theme of stellar death. And in that diversity, in that unexpected creativity, we find endless beauty and wonder. Let us now take a tour of some of the most famous and beautiful supernova remnants that we can observe. Each is a unique work of cosmic art, shaped by the specific conditions of its birth and the environment into which it is expanding. First, we revisit the Crab Nebula, the remnant of the supernova of 1054. Located in the constellation Taurus, about 6,500 light-years away, the Crab is one of the most studied objects in astronomy. Its intricate structure, powered by the central pulsar, makes it a cosmic laboratory for understanding pulsar wind nebulae, particle acceleration, and relativistic magnetohydrodynamics. When you look at the Crab, you are seeing the remnant of an explosion witnessed by humans not even 1,000 years ago. That sense of connection across time makes it even more special. The Veil Nebula is part of the larger Cygnus Loop, a supernova remnant about 5,000 to 8,000 years old, located roughly 2,400 light-years away. What makes the Veil so spectacular is its delicate filamentary structure. The shockwave has created incredibly thin sheets of ionized gas that glow in beautiful colors. The Eastern Veil and Western Veil are the most prominent sections, visible in small telescopes. In deep images, the entire loop can be traced, spanning several degrees on the sky. The filaments are so fine that they reveal turbulent instabilities in the shock front, showing us fluid dynamics at work on cosmic scales. The Veil Nebula is often described as looking like cosmic lace or an ethereal curtain draped across the sky, and it is easy to see why. It is breathtakingly beautiful. Cassiopeia A, or Cas A, is the youngest known supernova remnant in the Milky Way, with the explosion occurring about 350 years ago. Despite its youth, it was not recorded historically, likely because intervening dust dimmed it below naked eye visibility. Today, Cas A is one of the brightest radio sources in the sky and has been extensively studied at all wavelengths. The remnant shows a highly complex structure with fast-moving knots of ejecta, reverse shocks, and a central neutron star. Deep images reveal thousands of individual features, each telling part of the story of the explosion. Cas A is expanding so rapidly that its growth can be measured over just a few years, making it one of the few cosmic objects that visibly changes on human timescales. Watching Cas A expand is like watching a slow-motion replay of a stellar explosion. The Vela supernova remnant is one of the closest supernova remnants to Earth, at only about 800 light-years distance. It is also one of the largest in angular size, spanning about 8 degrees on the sky, roughly 16 times the diameter of the full moon. The supernova that created Vela occurred about 11,000 years ago, making it relatively old. The remnant is so large and close that it fills a significant portion of the southern sky. At its center is the Vela pulsar, one of the brightest pulsars and a powerful source of a pulsar wind nebula. The Vela remnant is best viewed from the southern hemisphere, and wide-field images show its full extent, an enormous bubble of glowing gas and complex structure. Because it is so close, Vela gives us an excellent view of the internal structure and evolution of an aging supernova remnant. The Kepler supernova remnant is the remnant of a supernova observed in 1604 by Johannes Kepler and many others. It was the last supernova visible to the naked eye in the Milky Way, making it historically significant. The remnant, located about 20,000 light-years away, shows a beautiful bubble-like structure in X-ray images. The expansion is highly asymmetric, suggesting that the supernova occurred in a region with uneven density, or that the explosion itself was asymmetric. Different elements can be traced in the X-ray spectrum, with iron-rich ejecta in the center surrounded by lighter elements. The visible light images show thin filaments where the shock front interacts with surrounding gas. Kepler's supernova remnant is a type Ia formed from an exploding white dwarf, giving us a chance to study this important class of supernovae up close. The Simi's 107 remnant, also known as the Spaghetti Nebula, is an ancient supernova remnant estimated to be about 40,000 years old. It is exceptionally large, spanning about 3 degrees on the sky, 6 times the diameter of the full moon. The explosion occurred relatively nearby, about 3,000 light-years away. What makes Simi's 147 so striking is its appearance. The remnant has evolved to the point where it appears as a tangled web of faint filaments, looking remarkably like strands of spaghetti scattered across the sky. The structure is incredibly complex, with loops, arcs, and twisted strands creating an abstract pattern. At the center of the remnant is a pulsar, PSR J0538+287, marking the location of the original stellar core. Due to its age and large size, Simi's 147 is quite faint and requires dark skies and long exposures to photograph well. But the results are worth it. The nebula looks like cosmic calligraphy written across the heavens. Beyond our galaxy, we can observe supernova remnants in nearby galaxies, giving us different perspectives and allowing us to study remnants in different environments. The large Magellanic Cloud, a small galaxy orbiting the Milky Way, hosts numerous beautiful remnants. N499 is a bright, roughly circular remnant showing a classic shell structure. N63A shows delicate filaments emerging from its center like flower petals. And of course, SNR. 1987A continues to evolve before our eyes, its expanding debris now illuminating the famous triple ring system. In the Andromeda Galaxy, observers have catalogued dozens of supernova remnants, though their greater distance makes detailed study more challenging. Each galaxy has its own population of remnants at various stages of evolution, creating a gallery of stellar death that stretches across the local universe. These remnants remind us that supernovae are universal phenomena, occurring throughout the cosmos wherever massive stars exist. Now we must ask a profound question. How have supernovae affected life on Earth? The answer is both inspiring and sobering. On the positive side, we literally would not exist without supernovae. Every element heavier than lithium in your body was created in stars or supernovae. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, the oxygen you breathe, all were forged in stellar furnaces and distributed by supernova explosions. Life requires heavy elements to build complex molecules, and those elements only exist because of stellar death. We are the universe's way of knowing itself, built from the ashes of dead stars. The very atoms that allow you to think and feel and wonder about the cosmos were created in cosmic explosions billions of years ago. You are stardust that has learned to contemplate stardust, but supernovae can also be dangerous. A supernova occurring too close to Earth could have devastating effects on life. The radiation and energetic particles from a nearby supernova could damage the ozone layer, exposing the surface to harmful ultraviolet radiation from the sun. Cosmic rays from the explosion could increase mutation rates and radiation doses for living things. The good news is that supernovae are rare and space is vast. For a supernova to significantly affect Earth, it would need to occur within about 30 light-years, and the nearest star capable of going supernova is much farther away. Still, over Earth's long history, there may have been times when relatively nearby supernovae affected our planet's environment. Some scientists have speculated that extinction events or periods of environmental change might be linked to supernovae, though the evidence remains circumstantial. The universe can be both creator and destroyer. Scientists have found evidence of past supernova impacts on Earth by studying isotopes. Certain radioactive isotopes that are created in supernovae but decay relatively quickly have been found in deep-sea sediments and lunar samples. The most notable is iron-60, a radioactive isotope of iron that does not occur naturally on Earth but is produced in supernovae. Deposits of iron-60 have been found in ocean floor sediments dating to about 2 to 3 million years ago, and again about 7 million years ago. This suggests that one or more supernovae occurred within a few hundred light-years of Earth during those times. The explosions were close enough that debris reached our solar system, but far enough that they did not cause major damage. These ancient supernovae left their calling cards in the geological record, cosmic messages written in exotic isotopes telling us that stars died in our galactic neighborhood in the relatively recent past. Looking forward, we can identify which stars might threaten Earth in the future. Betelgeuse, the famous red supergiant in Orion, is one of the closest stars that will definitely explode as a supernova. At a distance of about 600 light-years, it is far enough that the explosion will not harm Earth. When Betelgeuse explodes, and it could be any time within the next 100,000 years, it will become one of the brightest objects in the sky, possibly rivaling the full moon in brightness. It will be visible during the daytime for weeks or months. Imagine being able to see a supernova with your naked eye, to watch it brighten and fade over the course of months, to know that you are witnessing a cosmic event that humans have only rarely seen throughout history. It would be spectacular and completely safe, a front row seat to stellar death with no danger whatsoever. Bring it on, Betelgeuse. We are watching and waiting. Supernovae have also influenced human culture and mythology throughout history. The sudden appearance of a new star in the sky, where none had been before, was often interpreted as an omen or sign from the gods. Different cultures incorporated these events into their mythologies and belief systems. The supernova of 1054 was recorded not just scientifically, but also became part of oral traditions and was possibly depicted in rock art. Some Native American petroglyphs may represent the supernova and nearby crescent moon. The supernovae observed by Tycho and Kepler occurred during pivotal times in human history and influenced philosophical and scientific thought. These cosmic events occurring unimaginably far away reached across the void to touch human consciousness and culture. The stars have always been part of our story, sometimes literally falling from the heavens to remind us of our cosmic context. In our modern age, supernovae have taken on new significance as tools for understanding the universe and our place in it. The discovery that we are made of star stuff has profound philosophical implications. It connects us to the cosmos in a literal, material way. Every breath you take contains atoms that were once inside stars. Every time your heart beats, iron atoms created in a supernova carry oxygen through your body. This is not mysticism or spirituality, though it can certainly inspire both. It is scientific fact. We are not separate from the universe looking in. We are the universe experiencing itself. This perspective can be humbling and empowering at the same time. It suggests that consciousness and intelligence are natural outcomes of cosmic evolution, that the universe inevitably creates observers to witness its own beauty. Perhaps that is the ultimate purpose of supernovae, not just to create elements, but to make possible minds that can understand and appreciate what they have created. Supernovae also raise questions about the potential for life elsewhere in the universe. If supernovae are essential for creating the heavy elements needed for life, then planets orbiting first-generation stars, which formed from primordial hydrogen and helium, would lack the chemistry necessary for complex life. Life as we know it requires metals, in the astronomical sense of elements heavier than hydrogen and helium. This means that life could only arise after at least one generation of stars had lived and died, enriching the cosmos with heavy elements. The question then becomes, how metal-rich does the environment need to be for life to develop? Our solar system has a particular metallicity. Could life arise in more metal? Poor or metal-rich environments? These questions connect the physics of stellar death to the possibilities of life throughout the universe. Supernovae are not just about stars dying. They are about the universe becoming capable of supporting life, intelligence, and wonder. As we approach the end of our journey, let us reflect on the profound nature of what we have witnessed. Supernovae represent transformation on the grandest scale. A star that has shone steadily for millions of years suddenly unleashes as much energy as it produced in its entire lifetime, all in the span of seconds. Matter is torn apart and reassembled into new forms. Elements are created that never existed in that location before. Energy floods into space at the speed of light. And from this violence, from this destruction, comes the potential for new creation. Dying stars seed the cosmos with the building blocks of future generations. It is the ultimate act of cosmic recycling, ensuring that nothing is ever truly lost. Every ending is a new beginning. Every death makes new life possible. This is the eternal cycle that has been playing out since the first stars formed over 13 billion years ago. There is something deeply moving about the fact that supernovae, the most violent events in the universe, also create beauty. The supernova remnants we have explored are not just scientifically interesting. They are breathtakingly beautiful. Nature does not need aesthetics to function, yet the same physics that governs stellar death also creates structures of incredible visual complexity and appeal. The delicate filaments of the veil, nebula, the intricate web of the crab, the glowing shells of countless other remnants. These are works of art created without intention or design, purely as consequences of physical law. Perhaps this tells us something profound about the universe. Perhaps beauty is not something we project onto the cosmos, but something inherent in its fundamental workings. Perhaps the universe is beautiful because beauty emerges naturally from the laws of physics, from symmetry and complexity and the interplay of forces. In supernovae, destruction and beauty are inseparable partners. Supernovae also remind us of the immensity of cosmic timescales. The light from a supernova explosion travels for years, centuries, or millennia before reaching Earth. When we observe a supernova in a distant galaxy, we are seeing an event that happened when that galaxy was younger, perhaps before Earth even formed. The supernova that created the Crab Nebula exploded in 1054 as far as Earth observers are concerned, but the explosion actually occurred about 5,000 years earlier, the time it took light to travel the distance. The star died while ancient humans were just beginning to build the first civilizations, but the news of its death only reached us in the Middle Ages. Time and space are intertwined in ways that challenge our intuitions. Every observation is a look into the past. Every photon is a messenger carrying ancient news. The universe operates on scales that dwarf human experience, yet we can still comprehend and appreciate them. Think about the atoms in your body again. Each one has a history stretching back billions of years. A carbon atom in your hand might have been created in a red giant star 8 billion years ago, ejected in a planetary nebula, floated through space for billions of years, became part of the molecular cloud that formed our solar system, was incorporated into Earth, cycled through countless living organisms over millions of years, and now happens to be part of you. In a few years, that atom will likely leave your body and become part of something else. Atoms are borrowed, not owned. We are temporary assemblies of ancient cosmic material, patterns that persist for a while before dissolving back into the environment. Supernovae made these atoms available for this borrowing. They are the source from which all complex structures ultimately arise. In understanding supernovae, we understand the origins of everything we are and everything we see around us. Our exploration of supernovae reveals something essential about the nature of science itself. Through careful observation, mathematical theory, and creative thinking, we have been able to understand events that occur at distances and energies far beyond direct human experience. We will never visit a supernova. We will never touch its ejector or feel its radiation directly. Yet through the language of physics and the evidence of light, we can reconstruct what happens in exquisite detail. We can predict when stars will explode. We can explain the nuclear reactions that power them. We can trace the creation and distribution of elements. Science allows us to transcend the limitations of our senses and our lifespans to comprehend phenomena that dwarf us in every measurable way. It is one of humanity's greatest achievements, and it reveals a universe far more wondrous and stranger than any mythology ever imagined. The truth, it turns out, is more amazing than fiction. Looking to the future, the study of supernovae will continue to reveal cosmic secrets. Future telescopes will observe the first supernovae in the universe, exploding when the cosmos was only a few 100 million years old. These early supernovae played a crucial role in enriching the pristine primordial gas with the first heavy elements. We will discover new types of supernovae that challenge our current understanding. We will use supernovae as probes to study the expansion history and composition of the universe with ever greater precision. The next galactic supernova will be studied with technology that previous generations could never have imagined. And perhaps most exciting, as we extend the search for life beyond Earth, we will need to understand how supernovae affect the habitability of planets across the galaxy. Every answer raises new questions. Every discovery opens new frontiers. The journey of understanding never ends, and that is a beautiful thing. And so we come to the end of our journey through the realm of supernovae. We have witnessed the final moments of massive stars, watched as they collapsed and exploded with inconceivable violence. We have seen how these explosions create and distribute the elements essential for life. We have admired the beautiful remnants left behind, cosmic sculptures that glow for millennia. We have learned that we ourselves are made of stardust, that the atoms in our bodies were forged in stellar furnaces and scattered by supernova explosions. We are not observers standing outside the universe looking in. We are part of the universe, made from it, studying ourselves in a profound sense. When you look up at the night sky now, you will see it differently. You will know that the stars are not eternal, that some will die in brilliant explosions, that those explosions are essential for the existence of everything you care about. You will know that somewhere out there a star is taking its last breath, preparing to explode and seed the cosmos with new possibilities. And you will appreciate the profound beauty of this cosmic cycle of death and rebirth. Thank you for joining me on this journey. May the stars continue to inspire wonder in your heart. Our exploration of supernovae has come to an end, but their light continues to travel through the cosmos eternally. These magnificent explosions have given you everything you are, from the calcium in your bones to the iron in your blood. The next time you breathe, remember that the oxygen filling your lungs was created in the heart of a dying star. You are a child of the cosmos, stardust contemplating stardust. If this journey has moved you, consider subscribing to Cosmic Calm for more peaceful explorations of the universe's wonders. And may you always find beauty in the grand cosmic story of which we are all a part. Sleep well, dream of stars, and remember that you are made of light from ancient explosions. Good night.